And finally, there's one other place in the universe that we can go to look for specificity, and that's to look to life itself. Every living entity around us that possesses the spark of life is comprised of high amounts of specificity.
If you found an ancient clay tablet with strange characters washed up on the shore, you couldn't read it, unless someone had cracked the code. But you'd still know the letters represented a language, even if you didn't know anything else about the author or his civilization. Language is recognizable, even if you can't read it. Take Morse code. It has three basic parts: dots, dashes, and spaces. These three simple parts are combined to represent letters. There are 26 letters in the English language, which are combined to form over 400,000 words. Those words can, of course, be combined into an infinite number of sequences or sentences. There is evidence that DNA represents a language. 4 basic units, called nucleotides, combine into a code for 20 amino acids. From those few amino acids, the body forms more than 100,000 proteins. Even if you can't read DNA, it still has all the hallmarks of language, a language that biologists are just now beginning to crack. Every tiny cell in our body is packed with 3 feet of DNA, 3 billion nucleotides. The similarity between DNA and human language is uncanny. In addition to codes, both use similar techniques to pack, access, rearrange, copy, and translate information. DNA seems to represent a language, the language of life.
DNA is not simply a computer programming language, but as you have already seen, there are some startling analogies between DNA and computer code. We can view each cell as a CPU, or a central processing unit, running its own kernel. As you probably know, in computing, the kernel is the main component of most computer operating systems. It's a bridge between applications and the actual data processing done at the hardware level. So each cell has a copy of the entire kernel. But amazingly, each cell chooses to activate only the relevant parts, which modules or which driver it loads, so to speak. If a cell needs to do something or call a function, it calls up the right piece of the genome and transcribes it into RNA. The RNA is then translated into a sequence of amino acids, which together make up a protein for which the DNA coded. Now for the truly amazing part of the equation. This called up and coded protein is then tagged with a shipping address. This address is a marker consisting of several amino acids which tells the rest of the cell where this particular protein needs to be deployed. Once the protein arrives at its intended location, the delivery instruction is then stripped off and several post-processing steps are performed, activating the protein to now do its job. The protein is not activated until it arrives at its marked and intended location.